you will be able to direct them to a website where they can watch the webinar in its entirety. So once again, thanks everyone for attending. Let's begin. A little bit about our company. Electronic Data Solutions has been in business for 26 years. We offer a wide variety of hardware and software solutions, complete with technical support, training, seminars, and repair services. Our home office is located in Jerome, Idaho, which is in south central Idaho. And you can see that we currently have 8 offices in different states, providing services to our customers in a lot of different locations. The new Trimble Geo7X was released about 16 weeks ago. It began shipping the end of November. For the first time, it's a high accuracy GPS receiver that does have a built-in laser rangefinder. And of course, laser rangefinders are typically used in GIS mapping to help people remotely collect a point feature that they cannot directly observe. This particular product does include a cellular modem, and it's a universal modem, which means it can be activated on either AT&T or Verizon. It has 4 gigabytes of onboard data storage, and you can actually add up to a 30 SD card to that data storage capacity. It's got a full 1 gigahertz processor with 256 megabytes of RAM. And the nice thing about this particular product is that regardless of which level of accuracy you purchase, you can upgrade all the way to the top to the 1 centimeter unit. So in other words, if you purchase the Geo7X sub-meter, then you can upgrade to decimeter or centimeter. This new unit is a multi-constellation unit, so we refer to it as a GNSS receiver. And of course, GNSS is a global navigation satellite system. It picks up our US GPS satellites. It picks up the Russian GLONASS constellation. Naturally, it can receive corrections from the WASS satellite constellation, which is put up there by the FAA. It also picks up the European Galileo constellation and the Chinese Compass satellite system, in addition to the Japanese correction satellites. So it really is a multi-constellation receiver. In my personal experience, I've been outside with just the handheld and no external antenna in the open, receiving 22 or 23 satellites. This new unit also has a very unique feature. It's called SBAS Plus. And for those of you that might be familiar with this term, SBAS means a satellite-based augmentation system. And in the case of the US, those are our WASS satellites. WASS satellites do not provide positioning, but they do provide real-time corrections. So if you're out there in the field and you're picking up 7 or 8 GPS satellites, you can also pick up the WASS satellite constellation, and that will then apply corrections to your position. Now, what's interesting about previous versions of GPS receivers from Trimble is that the WASS satellites were only able to apply corrections to our GPS position. But the SBAS Plus now has the ability to use those satellites to provide corrections for all the satellites in view. So in other words, it applies corrections to the Russian satellites, the Galileo satellites, and the Compass satellites as well. There are some pretty nice sensors built into this new unit. It obviously has the laser rangefinder, which provides distance calculations, the clinometer, which provides the vertical angle, and the compass, which provides the horizontal angle. There's a very simple utility built into the software that allows you to do a very simple sensor calibration. We do recommend that you calibrate the sensors once in the morning before you start collecting data, and you should do this at the job site, not in your office. The multifunction measurements of this particular compass, clinometer, and distance rangefinder system allows you to do a single point feature offset, which means a single distance and bearing to a remote point feature that you're trying to map. It lets you do a multiple offset, which means you can occupy 1, 2, or 3 locations and then shoot the same feature. It also calculates heights, which means you can calculate the height of a tree or the height of a bridge above the water line, and you can also calculate what they call missing line. Now, missing line is a great feature because it allows you to shoot one object to your left, one object to your right, and it will calculate the distance between those two remote points in addition to giving you the basis of bearing. It's always good to talk about the accuracy because whenever you're applying an offset to a point feature that you cannot observe directly, it's very important to be aware of the errors that are built into those sensors. In the case of the distance meter, you have plus or minus 5 centimeters of accuracy, which means you're getting about 1.9 inches of error, just under 2 inches. So we do recommend that you keep the distances under 50 or 100 feet, even though the unit can shoot 400 feet without a reflector or 650 feet with. The longer your distance measurement is, the more error you'll have in your final solution. The clinometer has a ½ a degree of error, so that provides you with your vertical angle, which can help transfer elevations from one point to another. And then finally, you have the error in the compass, which is 1½ degrees. And of course, this is probably the most significant of all 3 errors, because what this means is that a 1.5 degree error will exponentially increase as your distance measurement goes away from the laser. So it's important to keep your shots fairly short in order to ensure high accuracy. Many of you are aware of this feature from previous models. The Geo6000 had this 5 megapixel digital camera, as well as the Geo7X does too. And the nice thing about the camera is that the laser aiming process within this new unit utilizes the 5 megapixel digital camera. So what this means is that you're not looking through an optical sensor. You're actually using the entire screen of the receiver to confirm that you're pointing at the correct target. Now, we couldn't show this on the screenshot for some reason, but you see the red dot on the screen. You can see that red dot on your target, and that is simply an aiming device or a pointing device. But in addition to that, you'll see a white square right in the middle of the screen, and that really serves as your reticle, as if you were looking through a rifle scope, so that you can confirm that you're hitting the right target. So it's a fantastic feature, and it allows you to simply press a button and take the measurement. If you don't like the measurement, you can erase it and take it again. As soon as you are confirmed that you're taking the correct measurement, you can hit the check mark in the lower right-hand corner of the screen, and you can save that measurement. Now, what's interesting about this, we do recommend that when you're beginning to develop your confidence in this measuring device, that you take several shots to the same target to confirm that you're getting good repeatability. And of course, when you hit that check mark, that's the shot that is recorded. One thing that we need to talk about when you're doing offsets is the total error budget. And this refers to the fact that if you have, let's say, the Geo7X H-star receiver, that's the decimeter unit. So let's say you're starting with 10 centimeters of error at the point of observation, then you have to be aware that you have 5 centimeters of error in the distance, a ½ a degree in the clinometer, and 1½ degrees in the compass. So it's important to keep all these things in mind. And we do recommend a very simple test. And that test is to observe something like a fire hydrant, let's say. So you hold the antenna directly over a large object like a fire hydrant, and you collect data for 10 seconds. You save that as a point feature, and then stand 25 feet away and shoot the hydrant as an offset point feature. Save that. Stand 50 feet away, shoot the same hydrant as an offset feature, save that, and so forth. And when you get done with this process, theoretically, what you'd like to see is all 4 point features would, of course, be on top of each other. But as we know, because there are errors in the various sensors, those point features will not be on top of each other. They'll be in, hopefully, a tight cluster. And by checking out which one had the 25-foot the 50-foot and the 100-foot offset, you'll be able to get a very concrete feel for what kind of accuracy you can expect when you're shooting various differences. So this is really an important process to go through, and this will definitely help you build confidence in the offset tool. So when should you calibrate? Well, Trimble does recommend that you calibrate the sensors once in the morning before you start your data collection day. It's good to stand away from large metallic objects like traffic control boxes, vehicles, trucks, anything that's large and ferrous metal, because of course that will affect the compass. It takes about 90 seconds, so it's a real quick process. In fact, you don't even have to look at the screen to perform the sensor calibration. You can even close your eyes, so it's a very simple process to do. And sorry, you can't shoot the offsets from your vehicle because that will drive the compass crazy. So you do have to stand away from large objects. So why are we talking about a centimeter? Because really our specialty in this industry is to help people collect data for GIS. And so why would somebody need a centimeter of accuracy for a GIS data capture project? Well, what's happening is that used to be in the realm of the survey division only, because obviously surveyors need 5 millimeters to a centimeter to do property surveys. But what's happening because of the convergence of technology and the fact that this technology is getting less expensive every couple of years, we now have customers that are demanding very high accuracy for GIS data collection. A great example, there's a city in the state of Washington who continually had to contact their survey department to help them get accurate elevations on the top of culverts, because they didn't have the technology to get that level of accuracy, so they had to continually talk to their surveyors to break them away from their regular routine so that they could provide this high elevation accuracy for them. Well, it turned out that when the centimeter unit was released, and this happened probably 20 months ago in a previous model, this particular city decided to buy the centimeter unit. And of course what that means is they can get 1 centimeter horizontal and 1.5 centimeters vertical, which was certainly good enough to get elevations on top of culverts so that they could confirm that they have the right percent of slope when they install these things. So there's a lot of good reasons to use a centimeter: aerial photogrammetry, LiDAR projects, precise staking and layout. When you compare the cost of an RTK system, that's real-time kinematic, which is a survey system, the top RTK system costs about $27,000 today. The same thing in a Geo7X centimeter system is around $16,000. So there is a huge difference in price between the survey 1 centimeter and the mapping 1 centimeter. And one of the big reasons for that is that surveyors are getting a lot of much more sophisticated software that folks in the mapping industry simply do not need. This 1 centimeter accuracy can be achieved in real time if you're picking up real-time corrections from a VRS or a single base. It can also be achieved by post-processing your field data as long as your base station is no farther than 16 miles away. So centimeter is making its way into a GIS workflow, only for some folks that need that level of accuracy. It allows the user to maintain the attribute-based data collection. So what that means, rather than collecting high accuracy data and only being able to type in a feature code, you have all the same facility that we've enjoyed for many, many years in able to create a feature name, and then you can describe this feature to your heart's desire. And you can say it's a hydrant, it's yellow, this is the manufacturer, this is the serial number, this is the brand name, and I'm actually going to add a photograph to my data collection as an additional attribute. So you have all the GIS functionality essentially with survey-grade accuracy. The Trimble floodlight, of course, and FlightWave technology. FlightWave is actually the laser. And floodlight is something that not many people know what it is. Floodlight is a marketing term that Trimble created a couple of years ago. And floodlight describes three extremely important functions that add a lot of features to this device. And the first feature in floodlight is the ability to pick up multiple satellite constellations. So that's the Russian, the Chinese, and the European constellation. The second part of floodlight is that there are algorithms that are built right into the receiver itself that automatically smooth out lines when you're collecting line features, and they smooth out the perimeter around area features when you're collecting polygons. The third function of floodlight technology is that there is a built-in electronic barometer in both the Geo6000 and the new Geo7X receiver. And the barometer, of course, measures barometric pressure. And when you have a barometric pressure reading and you combine that with the geoid model that is built into TerraSync software, it creates what Trimble refers to as altitude-constrained positioning. And this means that rather than getting 3 times the error vertically that you're getting horizontally, you can now virtually get the same accuracy vertically that you're getting horizontally. So it actually constrains the error in the altitude calculation so that in this particular unit you can get 1 centimeter horizontal and 1.5 centimeters vertical. So here's a polling question for everyone. Let me bring this up for just a second. This polling question says, how much would you benefit from using a laser rangefinder to collect points? So when that appears, go ahead and take a few moments and make a selection. Looks like 100% of everybody voted. Let me close the poll and I'll share that with everyone so you can see what the results were. Should be popping up on your screen in a moment. Looks like about 14% of you say that you would use a laser rangefinder often, and some folks, actually a preponderance of people, says somewhat often. This is interesting. I want to bring this up at this point. Just a couple of days ago, Trimble released a brand new price sheet which now allows you to purchase some types of this new Geo7X without the laser rangefinder. Currently, as of today, you can purchase the sub-meter version with or without the laser rangefinder. You can purchase the decimeter version or the 10 centimeter version with or without. The centimeter unit does come with the laser rangefinder. That's the only way you can buy it. But you do have the option on the slightly less accurate units. So let's move on. This is a great slide because this really describes what a VRS is. And the reason we talk about this is because in densely populated urban areas where you have good cellular coverage, and especially in states where a VRS does exist, this is an extremely powerful tool that will allow you to get high accuracy right in the field. And of course, we refer to that as real-time accuracy as opposed to post-processing. So here's what a virtual reference station is. It actually consists of a lot of survey-grade base stations and antennas. And all of these base stations are set up over known points. And you can see those known points are represented by the yellow triangles on this slide. Now this slide only shows 3 base stations, but as an example, in the state of Washington, there are approximately 100 of these stations. In the state of Oregon, there are approximately 100 of these stations as well. So here's how it works. Every one of these stations is sending its data to a central computer. And of course, that computer has an IP address or an Internet Protocol address. So if you're in the field and you have the ability to get to the Internet, and most people do that through a cellular modem, and that's exactly why a cellular modem is now built into this new unit, you then acquire satellites, and then you send a raw GPS position back to the computer as soon as you talk to it. So once again, it's going from the cellular modem to the cell tower, to the internet, to this single computer. And that's how you're contacting that computer. The computer sees where you are, and the accuracy of that position is about 20 to 25 feet typically. And so the computer says, okay, I see where you are within about 20 or 25 feet. I'm going to begin sending you a correction data stream that will apply corrections to your raw GPS position in the field as if the base station is only 20 feet away. So it then begins sending you correction data, which of course allows you to achieve unbelievably incredible accuracy in the field. So not only, this actually provides two different things. Not only does it mean that the user doesn't have to leave that location until they know they have the accuracy that they're trying to achieve, but it also means that when they come back into the office, there's no post-processing required. The data is ready to go directly into your mapping or your GIS program. So it's a very powerful tool. Now, the only requirement for this to work is, number one, you have to be inside the VRS network. So in the case of Oregon or Washington, where virtually the entire state is covered, then you can be standing anywhere within that state. However, the most important part of this, of course, is that you have to be able to get to the internet in order to receive these corrections. So the key is, can you get to a cellular tower? Now, for the folks that don't have a cellular modem built in to the device, you can certainly use your smart. You can use a little MiFi device, which will get you to the internet. So any way that you can get connected will allow you to receive these corrections. So where can you get 1 centimeter of accuracy? Well, if you've ever been surveying, or if you've ever talked to a surveyor who's been using GPS for some time, you know that they're carrier phase receivers, and they do have to see a pretty good view of the sky. What this means is you cannot get 1 centimeter in the woods. And the reason for this is pretty clear. A carrier phase receiver is actually counting how many of these 19 centimeter carrier wavelengths there are between every satellite in view and your antenna. And as soon as you walk under trees or you walk up against a building, you lose the count from several satellites. That counting has to begin all over again. So to optimize your 1 centimeter accuracy, you do have to maintain carrier lock as often as possible, and that means you have to maintain a clear view of the sky as often as you can. And if you lose lock, you can typically pick it back up again if you're willing to wait anywhere from 30 to 100 seconds at your next point of observation. In order to get 1 centimeter, you do have to use an external antenna, which is plugged in using a cable into the handheld unit. And we do recommend at least a 2-minute observation time on your first point. And sometimes it takes 3 minutes, sometimes it takes 4 minutes. But as soon as you achieve that level of accuracy, if you can walk to your next point without losing carrier lock, then you can achieve that same 1 centimeter accuracy instantly at the next point and the next point and the next point. So as soon as you lose lock with those satellites, you'll have to put in more time at the very next point. So here's how you can get corrected data. We've already talked about this to some extent. You can use a VRS to get real-time network corrections. You can also do post-processing. Now, because you're trying to achieve 1 centimeter of accuracy, you have to be no farther than 18 miles to your base station, which is 30 kilometers. I mean, you do have to be fairly close to a base station. However, if you're in a VRS network, it doesn't matter how far away you are because you're actually receiving multiple correctors from multiple base stations all at the same time. And because of that additional redundancy, your distance from a base station isn't so important as it is receiving those multiple correctors. If you're in an area where it's extremely difficult to get to the internet, we do have a solution for that, and that's called the Intuicom RTK base. And I've got a couple of slides near the end of this presentation to show you what that is and to kind of explain how that will help you. So here's a very important issue. What software should you use, or do you have to use, in order to use 1 centimeter accuracy? Well, you do have to use the Trimble Centimeter Edition software program. The centimeter accuracy is not supported by ArcGIS Mobile. It is also not supported by ArcPad. So you do have to use the Trimble TerraSync software. What's interesting about this, though, and for those people who are currently using ArcPad or ArcGIS Mobile on maybe a submeter or maybe a decimeter unit, even though you do have to use the TerraSync centimeter software, you put that data into Pathfinder Office. Pathfinder Office now has several alternatives on how to get that data into your GIS. The way that you're all familiar with is to export to shapefiles, and that's been around for about 20 years. But the new way to do it is you can export from Pathfinder Office directly into a file geodatabase. So that allows you to skip the shapefile export altogether, and it does make it much easier for the GIS person to take the data out of Trimble software and put it into their geodatabase. So horizontal versus vertical. TerraSync software is the only software program of the ones that we just mentioned, excuse me, that uses what they call a geoid model. A geoid model is a model of the Earth based on gravity readings, and the gravity model mimics mean sea level. So all data with a GPS receiver is collected in terms of latitude, longitude, altitude, height above ellipsoid in meters. So the ellipsoid is a calculated shape of the Earth, much like a beach ball, and because that doesn't relate to mean sea level, that data somehow has to be converted from WGS84 to a mean sea level datum. And in this particular case, because TerraSync contains this very important geoid model, it's able to do that conversion right on the fly. So it will convert the HAE to mean sea level, giving you highly accurate elevations in the field. If you're picking up real-time corrections, it'll give you highly accurate elevations in the office if you have to post-process. So ArcPad and ArcGIS Mobile, even with Trimble positions, does not contain this very important model. So that's the reason that TerraSync Centimeter Edition software is required. A little bit about the accuracy for this particular unit. You can use the Centimeter Edition Geo7X receiver all by itself without an external antenna. If you do that, you will get approximately 3 centimeters of horizontal accuracy. Now that would be rather strange because there's no way to know exactly where you're holding the antenna to get that accuracy, but just let you know the antenna that's built in is a very high quality antenna. But in order to get the 1 centimeter, you do have to use the Zephyr Model 2 antenna, and that's a survey grade antenna. So here's our second polling question. This polling question asks, obtaining 1 centimeter of accuracy would allow me to do which of the following? So go ahead and take a few moments and make your selection. Okay, it looks like everyone's voted. Let me close this poll and share it with everyone. You can see what everyone selected. That's pretty impressive. It looks like almost half of you would be able to provide a better, higher accuracy product for your clients, and I think that's really what a lot of people are thinking now, is that if you have to go out there and collect the data, you might as well get the best accuracy possible, especially if the project requires it. You would be able to respond to contracts that require higher accuracy, of course, and 14% of you said all the reasons above. So that's great. I appreciate you taking the time. So on to the item that I mentioned a little earlier, the Intuicom RTK base. There's really two different pieces that comprise this interesting solution to getting to the internet. There are places out there in the field, and you've all been there, where you simply can't get a cell signal. And of course, if that's the environment that you're working in, then of course you wouldn't be able to receive these real-time corrections. However, there is a company called Pacific Crest Radio, and Pacific Crest makes a radio that can be plugged directly into your handheld receiver so that it can receive corrections from the RTK Intuicom base, which I'll show you in just a second. And it actually uses a 403 to 473 megahertz band, which is considered to be a terrain-following frequency. And that means if you're picking up a radio signal that has a long wave, it's able to hug the terrain and travel over longer distances. So theoretically, you would buy one of these radios and plug it into your handheld unit that's attached to the pole that is supporting an external antenna. And then in addition, you would have this Intuicom RTK bridge, which would pick up a super weak cellular signal. In fact, this unit picks up a signal so weak that your cell phone would not be able to see it. So here's how this works. Theoretically, you have this Intuicom RTK bridge. You put the unit inside your vehicle, which is parked on top of a hill near the project site. And of course, the reason it's parked on a hill is because that's where you can pick up a super weak cell signal. There's an external antenna that can be stuck on the outside of your vehicle so that you can make sure that it's as sensitive as possible. And then this RTK bridge will then take that weak cell signal, it'll amplify it tremendously, and it will rebroadcast it out on the same frequency that the Pacific Crest radio can receive. So what you're doing, you're going to an area where hopefully you can pick up a very weak signal, it'll be amplified, it'll be rebroadcast, and that cell signal will then be received by your GNSS receiver, in this case the Geo7X Centimeter Edition, and it will provide you with that 1 centimeter of real-time accuracy. So you can now theoretically connect to the outside world even though you're miles away from what we would consider to be a strong cell signal. Here's a photograph of a guy who's in the field using it to follow a transmission line. And you can see that he has the RTK bridge sort of set up on a little tripod. One of the antennas picks up the cell signal. The other one will rebroadcast it. And then you can see he has the Pacific Crest radio on his range pole mounted just underneath the handheld unit. So let me give you a little closer view of what that picture reveals. And of course, by the way, the distance, the average distance between the RTK bridge and the Pacific Crest radio is about 1.5 miles. So you don't have a 5 or 10 mile range, but you do have a pretty decent range where this base, so to speak, can get that signal out into the project area. So here's our last polling question, and then we will wrap up the webinar. This last question says, if I used a centimeter mapping system, I would be able to do what? So here's our last question, and then we'll open this up for questions. Okay, everybody voted. Thank you, guys. Everybody's participating. That's great. Let me share this poll so you can see what you all said. Looks like once again almost half of you would rely on post-process corrections, and of course to get a centimeter in post-processing, that base does have to be, the base station that you're using does have to be within 18 miles of your project site, so that is a limitation. But almost half of you said any two of the above as well. So that's great. I appreciate you taking the time to answer that. So here's our last thing, our questions and discussion. It's going to take me just a couple of seconds here to unmute everyone. So let me do that real quick. Okay, everybody is unmuted. If you have any questions or comments, please feel free to just speak out. Okay, well, if there's no questions, here's our contact information. I want everybody to have this because you're probably attending from different parts of the country. Jackson Bigley is our representative in Missoula. He takes care of Montana, I believe Utah, parts of Colorado, Wyoming, and the most eastern parts of the state of Washington. I take care of Alaska, Western Washington, Western Oregon. Chase takes care of Idaho, and Sean takes care of California. So if you guys have any questions, just jot down those phone numbers and those email addresses. I'll be happy to take any questions offline. And I want to thank you very much for attending the webinar. I hope this has been informative. We rent and sell all these products, so if you have any questions or would like to try them out, please feel free to let us know, and we'll be happy to help. So thanks very much for attending. Give me a call if you have any questions.